have here the candle flame. And that candle flame is shooting light out, sending light out equally in all directions, or except straight down, the candle's in the way. But anyway, the influence of the light goes off in all directions. You will find when you study light that the intensity of light varies as the inverse square of distance. You will find when you study radioactivity that the radioactiveness varies as 1 over the distance square. You will find out magnetism with a magnetic pole here, that the magnetic field strength goes off as 1 over the distance square. You will find out when you talk about electricity, and you've got a charged object here, that the further and further away you get, the electrical influence peters off as 1 over the distance square. All through physics, you'll see something over the distance square. And I want you to see that that's intuitive. We'll do it now for the case of light. Let's suppose this eraser is a piece of photographic film, and I hold that photographic film right here. There it is, okay? I'm catching light. In fact, a shadow's cast, isn't it? I'm catching all the light that comes in here and out to here. I can't draw this part out here, okay? But that's how much light I'm catching. And let's say I'm a particular distance away, and I'll call that distance to there. Okay. The question is, if I get twice as far away, will I catch less light or more light? Because if I hold it here and I bring it into the darkroom and develop it, the film there is going to be darkened there, isn't it, with a light hit? How about if I held the film twice as far away? Twice the distance. It's about here. Oh, look at this. Out here. This could fit in the shadow. I could get 2 erasers in the shadow. Could I get 2 erasers in the shadow or more? In the shadow cast by this. Some people say, oh, 2. I can see 2. 1 here and 1 there, and that's the end of it. And other people say, no, 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 no. You get more than 2. More than 2 erasers will fill the shadow. See if your neighbor knows. Begin with F, end with or. 4. Excellent. All right. Because you could get 1 here, 1, and out like this too, see? It's sort of like that, like 3D. So you know what? 1 eraser here would catch 1/4 as much light as if it were here. Do you see that? 1/4 as much, because the rest is going here, here, here. So 1/4. Let's suppose I get 3 times as far away. That's about out to here. Out to here, that about right? 1, 2. I'm not sure if it's drawn to scale again, but over here I get, look, 1, 2, 3. I can get 3 erasers. So someone say, gee, 3 times as far away, 1/3 the light, because this would get 1/3. The rest would go up here. 1/3 is wrong. What's the answer again? Neighbor. It's a 9th, ain't it? Huh? So you get like this. See that? See this eraser? Here it is over here. It's only getting 1/9 the action, because the rest is all coming out here. And so then I could say, what if I put it 10 times as far away? And you guys would say, hey, it's not catching 1/10 the light, it's catching 1 what? 100th the light. Because 10 times as far away, I could have 100 erasers fill up the shadow that this one took. 100 erasers would be required to catch all the light that this one here caught. So the intensity out there would be 100th. Well, guess what behaves the same way, gang? Begin with a G. Gravity. Philip von Jolly suspended a mass from an equal arm balance and balanced it with some little weights over here. And then what he did was he rolled underneath it a great big 6 tons of lead of mass 2. And when he did that, guess what happened to this nice balance? Take one guess. How many say nothing? How many say something but a little bit? Yes, something a little bit. And what happened is that comes down. And when that comes down, then he puts another weight over here of known force to see how much it takes to restore balance. Knowing this mass, and knowing the distance between, von Jolly was able to, with all these measurements, calculate that force divided by the mass, other mass, distance square, was able to calculate a number, and that number turned out to be 6.67 times 10 to the minus 11th. And you know what? Makes no difference what values of mass or what distances you consider. You'll always get the same number, and that we call G. And G has units: newtons, Kilogram square divided by meters square.
All right, there's that mass, by the way. It's right there.
You're driving in a car, your friend's car, and your friend says, hey, I want to do something different today. And you're driving, all of a sudden, different. And as you fall down, is gravity pulling on you? How many say, oh no, gravity ain't pulling anymore. Gravity gonna take a holiday because you is moving. Stand up, I want to see what you look like. Nobody say that. You know gravity pulling on you, okay? But you don't feel it. You know why you don't feel it? Because there's no more support. When you're riding in your friend's car, steady speed, huh? And you're sitting right down, you're scrunching right against the bathroom scales. Those bathroom scales are supporting you, holding you up. Now, when that car goes off the cliff, you look down at the bathroom scale, you want to read the force of gravity, but what do you read, gang? You read 0, because you and the bathroom scale are both falling together. And so you feel what you call weightlessness. In physics, we say there's an apparent weightlessness because there's really a gravity force acting on you. Okay? But it's like this. I got here this ball. Okay? You're in an elevator. You're in an elevator, and all of a sudden you're holding a ball up like this, and someone cuts the cable. And as you're falling down, it seems to you like someone cut the gravity off. Watch this. I hold the ball in front of my face. I step off, let go, and it's still in front of my face. Okay? Now, why did it stay in front of my face? Now, if you want to try this and you want to really get the effect, jump off a very, very tall building. And as you jump, you go, son of a bitch, hey, there's no gravity act. There's plenty of gravity acting, okay? The thing is, you're both falling together, and it feels like there's no gravity. Talk to an astronaut type who's been in orbit. Guess how they feel? The same way you feel when a car goes over a little lump like that. Also, you're not supported for a moment. You feel that little queasy feeling? They feel like that all the time. That's why they bring barf bags. People in the space shuttle. You look up in the space shuttle. Your friends say, hey, look at those dudes up there, honey. They got no gravity. They get no gravity because they seem to be floating around. They take this ball out, let it go, and just hover right there. Take a pen out like that. It just kind of floats in front. It looks like there's no gravity because the TV cameras inside are recording that. And they see the astronaut type like that, and they see it floating like this. Hey, no gravity up there. It's a common idea that there's no gravity up where the satellites are. What do you guys say? If you use that equation to guide your thinking, D up there is not very much bigger than it is down here. That D is toward the center of the world. Newton figured that out. When you want to measure the force of gravity between you and the world, you take the distance between your belly button and the distance to the Earth's belly button. That's the center of mass. That distance. And when you go 100 miles high, honey, that's not much more than the 4,000 miles you are to begin with. So they have just about as much gravity up there in space shuttle territory as they do down here. But those video cameras make it look like gravity's been cut off. Much of the public does not understand that. We do, because we are a little more educated than much of the public. Is that true? Do we see that, hey, everything is falling together, huh? It's falling around. Some people thought that gravity was rather local, and some evidence for that was back in the early 1700s when they looking at the planets. The astronomer types know that when a planet goes by Jupiter, for example, the planet coming around the sun like this, when it goes by Jupiter, it sort of wobbles a little bit. And that was to be expected because there's an interaction between the planet and Jupiter too, like the planet Uranus, okay? But when Uranus is way out here and Jupiter's over here, they found out that Uranus was acting a little differently out there too. They called that a perturbation. And they found out that the planet Uranus was undergoing a perturbation where no other planet was. And the popular idea at the time was, well, way out there, the law of gravity, Newton's majestic law of gravity, is obviously breaking down. But not everyone believed that. A couple of mathematician types made some calculations as to where another planet would have to be to cause those perturbations. And they made about the same time in history. One was an Englishman, the other one was a Frenchman. And the Englishman reported his hypothesis and sent it to the observatory in Greenwich, England. When the observatory type got his letter, opened it up and says, what's this? Some mathematician is telling me that there's a new planet, so-and-so coordinates in the sky. What is this stuff? I'm exaggerating. The Frenchman sent his findings to the observatory in Berlin. And the Berlin types said, what's this? A new planet? If I turn my telescope so many degrees that way and so many degrees, I will find a new planet? Son of a bitch. There it was. They discovered a planet predicted by the law of gravity. And that planet they called Neptune. That's right. Neptune was predicted. That's the nice thing about science. If you know some science, it will allow you to predict things.